Hello, everybody. Welcome to today's episode of iCANX Talks. And I'm very happy to announce that it's going to be a beautiful molecular electronics party. I am today's moderator. My name is Christian Nijhuis from the University of Twente, chairing the group of hybrid materials for optoelectronics applications. These are the speakers of this month. Today we have Ayelet Vilan speaking. And today's topic will be related to molecular electronics. But keep your eyes open also for next week's contribution from the Weizmann Institute. And perhaps maybe also for a personal reason, because iCANX is also about connecting people and about family ties. The last speaker of this month will be Michael Dickey, and he will be likely talking about liquid metals and how they can be applied. We have been both postdocs in a group of Whitesides at the same time. That's why we know each other very well too. But back to today. Today's speaker is Ayelet Vilan from the Weizmann Institute. And these are the panelists: Martin Thuo from North Carolina University, Gunlan Guo from One University, and Xiyu from Tianjin University. And we share all, very importantly, one important thing, our passion for molecular electronics. So Ayelet Vilan, she is based at the Weizmann Institute in Israel. And yeah, I can say she's an expert on theory and how to extract enormous amount of information from experimental data. She was for a little while at Eindhoven at Philips before she returned to the Weizmann Institute in 2005. And of course, that is something I'm very happy about, given that I'm Dutch myself. She is developing empirical tools for the interpretation and quantification of charge transport across molecular junctions, and it can be both in single molecule configuration or in a configuration of large areas molecular junctions. And I think she's going to be talking about both today. I think for whom, especially those that regularly tune in on iCANX, yeah, I think you all know Martin Thuo. I don't think he requires any form of introduction anymore. He has been, I think, one of the most active members of iCANX. Our younger panelist members is, for instance, Gunlan Guo. She is these days based in One University. But also personally, we have a small connection because I met her for the first time when she was a postdoc, also at the Weizmann Institute, with Professor Schäfers and Professor Kahen. And there she has been working a lot on molecular electronic tunnel junctions as well. So I'm very happy that she's here today. And our second panel member is Xi from Tianjin University. And he too is not an uncommon name in molecular electronics. Also, he studied a little time at the Weizmann Institute as a postdoc. So I guess we can say this today also maybe a little bit of a Weizmann alumni gathering. But he also spent some time at MIT. So he's quite well accomplished. These days, he's a professor and and he's regularly publishing in all the kinds of top journals. So I'm also very happy to have him here on board. So I have already introduced all the speakers. So let me, go back here. This is the slide I was looking for because this is now the opening for Ayelet Vilan. Ayelet, please, you can now start with your talk. As mentioned before, you have about 60 minutes, followed by about 30 minutes of Q&A. Please start. Yeah.
Okay. Thank you very much, Chris. Can you see my, or I should share it now? No, just this.
Yeah.
Okay. So thank you very much for the audience who come and for Professor Zhang for inviting me for this very nice occasion. So as introduced by Professor Naya, I will talk about molecular electronics, but I would like to give it a little twist or a unique aspect that I will talk mostly about electrostatic effects, which I think are not so common in this discussion. Sorry, page. Okay, so why molecular electronics at all? So generally, we can think about three sources why we are interested in molecular electronics. One of them, or the most historical one, is the evolution from inorganic electronics, where people wanted to basically to search for ultimate miniaturization, to the smallest possible particle that can make electronics. So molecules are smallest objects. The other strong motivation is the fascination from biology, where people would like to mimic biology and learn from the very efficient processes biology knows how to do, like energy conversion, or maybe to do different sensor for future healthcare and so on. That could be another direction for molecular electronics. And the one that is very popular these days are towards quantum computation, because molecules are quantized objects. And in fact, I think most of the community from molecular electronics these days is mostly interested in these quantum aspects and looking for quantum effects. But the claim I wish to make is that the other two directions are much more about electrostatics. So both biology works with potentials, and also the devices, diode and traditional devices, are basically based on a potential state. So in this regard, I think the electrostatic aspects are very important, but they normally don't get enough attention as they should. So this is the main motivation behind my talk today, to give more aspect on these, more focus to electrostatics. Of course, the other transport effects and phenomena is very important, but I just want to give a different viewpoint. Yeah, that's what I just said. So I would divided the talk to three general topics. I'm not sure I will get to the third one, but first of all, to talk about interface barrier, potential barriers. And then I would like to talk about how much the interaction between a molecule and an inorganic substrate actually changed the molecule. And the last, I would try to, if I have enough time, I will talk about what can we learn from the voltage effect by changing the voltage. Voltage is another electrostatic aspect that we change the voltage. So I will start with using molecular monolayers to modify the potential barrier at interfaces. So this is a quote. The interface is the device, is a quote from Herbert Kromer, Nobel laureate from 2001. And why he argued that the interface is so important. So let's start from an interface between two chemical materials. And at the interface, we have different chemical potential at the two sides of the interface. And the chemical change make a change in the chemical potential. And this change in chemical potential translate into a change in the electrical potential. And this electrical potential, this change is what I call the electrostatic effect. Okay, so by chemistry, we can make a huge electrical effect. That's the general concept behind. And for example, so if we take a what's called p-n junction, a diode, or a junction between silicon that has a p-type doping, which shown here by the boron. So we have a missing electron here, that would be a p-type. And on the other side, we have an n-type silicon, and with an extra electron due to the phosphor doping. So there is an interface, and at this interface, we are changing the electrochemical, the chemical composition is expressed as a change in electrical potential. And Aviram and Ratner already 40 years ago, almost 40, yes, 50 years ago, followed this idea, and by this idea of miniaturization, so we can take this change in chemical potential into its ultimate miniaturization by using molecules. And that was their basic idea. And the point I want to make, that's also their paper is looking at this energy or potential difference and not so much about quantized effect and resonances. So in a way, we can think about it as like engineering, nanometric engineering. So I give here an example of water. So if we put a dam, we can use the water potential to make energy. But on the other end, we have interfaces where we want it to be very flat. This is a Roman engineering. This is antique from Israel, where the Roman used to make these bridges to transfer water for long distance in the desert. And so sometimes we want the potential to be very flat, and in other cases, we want a very sharp potential change. And that's also true for interfaces. So an interface with a strong potential difference would have like a diode. It's a asymmetric transport, and a very flat interface would behave as a resistor or an injecting interface, which is also very important. And this ability to modify the interfaces has numerous application and relevances. So here are a few examples just for solar cells. So the efficiency of a solar cell is if we can make the active interface to be as high as potential energy as possible. But on the other, there are many other interfaces that should be flat, that we will not lose energy on them. In the smallest the particles, like nanoparticles in 2D materials, the interface become more and more important because of the high ratio, volume to surface ratio. And of course, for sensor and everything. So all this engineering, so the idea is that for silicon, which I started with, the problem is relatively solved. But as we want to develop new materials and new application, we need to learn how to control these interfaces. So my talk will be very theoretical or principal, but there could be a lot of implication for these findings. So this interface potential, some references or in the literature, you can also look at it, people call it electret, where electret is like the potential or the charge analog of a magnet, where we have a layer of the material is polarized by two ends, but we can really make this electret as seen as a nanometer, 1 to nanometer. And the way we do it is using molecular monolayers, and that's also was displayed in this series by the two other people here in the panel. So we start with a substrate, with a conductive substrate, and we bind a molecular self-assembled monolayer onto it. And it will have a binding group and a tail group, which are normally different. And then because of this different chemical potential of the two ends, we have normally there will be some dipole along these molecules. So in this example, one side, let's say, is positively charged and the other is negatively charged. And this separation of charges will cause a dipole. And I will follow the notation that the dipole is pointing to the negative pole. There is a mixed notation. Some people use opposite. And as a result, this area of dipoles translate into a potential difference, depending on the density of the dipole, the magnitude, magnitude of the dipole, the angle, and the dielectric constant. So all this will define the dipole or the potential difference. So delta would be the potential difference due to an array of dipoles. And after doing that, we put the top contact, and that will make an interface. Okay, so we're starting from a surface and then making an interface, and I will make an interplay between the surface and interface measurements and an array of dipoles. And in general, we are not talking about ionization. So there could be ionization, but not necessarily. Normally, just polarization of the molecule, no extra charge. Yes. That's what they said. This is the theoretical work, not for me, but just to show that the idea that if we have a single molecule, which is polarized, but then we add its neighbors, so the field line, these arrows show the field lines, they would cancel each other. So the electric field for a single molecule shown here is rather slow. It's changing very moderately. However, when we have this area of dipole, we have a very intense electric field, much stronger than for a single molecule. And this is very important to remember because not all the lessons that we know from an array. The array has a very important electrical implication. It's not the same as with single molecules. So some effects that we see with the monolayer we will not see with single molecule. This is another simulation, not from our group, from Zoyer, and they show they simulated the electrical potential. So they show that around the molecule there is a dip in the electrical potential. This is not shown here. This is naphthalene with thiol and cyano, or biphenyl, sorry. But if they put an array, there is a very clear step in the potential. So an array of molecule would make a very clear step, as shown here, but a single molecule will not, and this is an important point to keep in mind. So another thing from that talk for Palmer that I like very much is that we have to start from an energy band diagram, and I will now just walk you through this energy band diagram. And that's again how do we understand the potential mapping or something like that. So we start with the metal. The metal is filled up to its Fermi level, drawn here. And then it has the vacuum level. The vacuum level is the energy of an electron just outside the metal. Okay? And the difference between them would be the work function. Now we bring a different bulk material like a semiconductor. The semiconductor is characterized by a forbidden energy gap. So electrons can be either at the valence band, or if we give them extra energy, they would be in the conduction band, but there is a gap here with no electrons. And then if the two materials are in electrical contact, their Fermi level is equal. However, as we put them into contact, and on the difference between the two so the different materials would have a different energy to take an electron out. So in general, the work function is different for different materials. And the difference between them, we call it the contact potential difference, or CPD. This is shown here. Now, if we bring them into contact, also their vacuum level should be the same because they are in contact. And then the CPD should be spread somewhere. So it normally spread on the material with less electrons. So the metal has many electrons, so it can screen very easily. So the CPD falls in the semiconductor side. And as a result, there is a charge in here, okay, in the semiconductor. And there is this potential difference, I will call it the Schottky barrier height, this psi here. And it's ideally just the difference between the work function of the metal and the work function of the semiconductor. That's the general theory. But now notice the distances. This we will consider. So the space charge region, this region here in yellow of a semiconductor is the order of hundreds of nanometers. Okay, and we're talking, I will show in a moment, molecules which are around 1-2 nanometers. So now what happened when we apply a voltage? So when we apply a voltage, we change the Fermi level. So when there is a voltage, the Fermi, here it's a 0 voltage, the Fermi level is constant. When we apply a voltage, positive voltage on this metal side, the semiconductors goes up and the electrons will have less and less barrier to cross. So that would be a lot of current cross easily. However, in the reverse voltage, we bring the metal up, and from electron to cross from the metal to the semiconductor, they will always see this psi. So this potential barrier would always remain in the reverse, but not in the forward. Okay, so that's the basic idea behind this asymmetry in transport. So that was general theory, and now we start to play with it and put molecules inside. So I give an example of a styrene, a substituted styrene molecule on silicon. They bind, there was a double bond here that is binding with UV light, and it's H-terminated silicon. There is no oxide here, direct binding. And we compare 3 different molecules, so it's not a mixed monolayer. It's either with methyl termination, bromine termination, or non-substituted. So it's 3 different monolayers. And this is the IR spectroscopy of these different monolayers. And we can see, for example, that this CH time, that's the reversion here on the styrene, is really changing. So the shift in the IR already tells us that there is some change in the electric field. So that the internal electric field in the monolayer is changing by the substituent, and then we see a very strong shift in the vibration strength. And in quantitative organic chemistry, the change in the polarizability or the reactivity of phenyl ring is often measured by a parameter called Hammett. This is for general synthesis, organic synthesis. And it has these different parameters. It could be different types of chemical effect, but I would take here this sigma, which is called the inductive. So like what the effect of the, not coupling or anything like that, but just electrostatic effect, which is basically what we are looking for. The other thing that I will next do is just to measure how these molecules change the work function of the silicon. And we measure it by a Kelvin probe, a technique called Kelvin probe, but many of you may know it from a conductive probe AFM, but we measure it with large area, but it's relatively the same technique. So this plot shows the contact potential difference, what I just described in former slide, against the Hammett parameter, and this is tabulated data. So the Hammett parameter is tabulated for these molecules, and we see a very nice correlation between the change in work function and the chemical nature of these molecules. So it basically shows the same principle that I showed from the beginning, that we translate a chemical property like the Hammett parameter into an electrical property. In the difference in the contact potential difference, and the difference is quite large. So as a thumb rule, the band gap of silicon is 1 electron volt. And we see a change of about from minus 0.7 to plus 0.3. So the change is almost as large as the band gap of the silicon. It's a large change. It's a very strong effect. So this is basically, if we go back to the energy diagram, this is what we are seeing. So if we have the methyl termination, it reduces the CPD. So it's like the work function of silicon is going down. And for the bromine, it increases because it's negative. Okay, halogen has a negative charge, methyl is electron donating, so it reduces. That is what we expect. And the next step would be to put a top contact on top of it. And again, it was in the talks of Professor Nijhuis and Tuho. They are using liquid gallium indium. Here we are using mercury, because mercury is immiscible in silicon. So the choice of top contact should also consider the top and bottom contact should be immiscible. Otherwise, there would be diffusion through the monolayer and shortcuts. What we have found is actually there are, because silicon is so much studied, there are few metals that are immiscible, quite a few. Most of the metals are miscible in silicon, but these bunch of elements are immiscible. So we also, so like mercury, we tried also lead, and it was possible to evaporate lead on these monolayers, and this is a high resolution TM cross section. I think it was just the simple styrene here inside, and we see very nicely the atomic planes of silicon, the atomic plane of lead, and in between this 1 nanometer. Of course, TM is not a good indication that we don't have shortcuts because it's very on a very small area, but it is possible to use one of these two methods with silicon. So I will show now the IV results for still measured with mercury, not with the lead. And this is a semi-logarithmic plot of current as a function of voltage for the 3 different terminations here. And we see, first of all, that the non-substituted and methylstyrene have a very asymmetric transport. So they have like a diode. And the bromine is completely symmetric. This is here on a linear scale. So we see the bromine is really like a resistor. This is what I started with. So this would be like a resistor, and the methylstyrene would be a diode-like. And notice also the orders of magnitude. So it's about 7 or 8 orders of magnitude difference. This is huge by only a change if 1 atom at the end. But it's important to stress that this change is because of the silicon. So what blocks the current is the silicon, not the molecule. There are molecules, the only thing they do, they make an electrostatic effect. So again, this is the same diagram that I showed before, and this is just explain the forward and reverse, why there is an easy current in the forward bias and there is no current. It blocks the current on the reverse. And the key parameter is this psi, the potential difference here. And we said that theoretically it's just the difference in work function. Okay, so let's see now why the molecules are changing this. So again, we start with the metal, we take the bromine, and we said that it has this dipole that's going up. And I will do again the same energy diagram. And so then upon contacting, what happened now is that the bands of the bromine, the silicon underneath the bromine is bending downward. And on the other end, when we have a metal with its lower work function, the bands in the silicon are bending upward. This means that under bromine, the silicon will have a lot of electrons, and this is all my examples are with N-type silicon, so the Fermi level is close to the top of the gap. So back in the silicon, there are a lot of electrons. So if also at the surface there are a lot of electrons, it basically behaves like a metal, and that's why it's linear. So it behaves like a metal. However, if it's highly bent, the levels, it means that at the surface we have a lot of positive charge. There are so much positive charge that there are even holes, like the opposite. And just by this 1 nanometer monolayer, we were able to make a PN junction without any P silicon. All the silicon is N-type. But because of this huge electric field over the methylstyrene, the surface become P-type, and this is called inversion. There is also an intermediate regime called depletion, but inversion is really a lot of devices like lasers and light emitting diodes. They are all working under inversion. So if we are capable to reaching inversion is technologically very important. And that's basically, again, that's guy Herbert Kromer, that's what he got Nobel for. And the normal technology doing it just by combining different material with MBE and very expensive deposition technique. And what we showed here that with this very soft and allegedly fragile molecule, we can get an effect that is similar to what people get with MBE and high vacuum deposition techniques. So in summary, for this part, the entire discussion that what I showed now was that we basically, the self-assembled monolayer is electrostatic modifier. We ignore its effect on the transport. It may have, but the effect of the silicon is much larger. This interplay between the tunneling in the molecules and the blocking by the semiconductor space charge region, that this space charge region, it can have, again, very interesting nonlinear effect and so on. There's a lot of rich possibilities there. And the thing that fascinates me is that we put a 1 nanometer SiC potential step, and it can control hundreds of nanometer potential difference in the semiconductor. And that's, again, something that molecules are really strong. So we think about molecules as something fragile, but in terms of their ability to hold electric field, they are much more rigid than inorganic materials. And it's important I would like to stress the difference in the polarization mechanism. So we're talking about electrodes. So in the inorganic silicon, the ionization is by accumulation of ions and possibly free carriers like electrons or holes. In the molecules, on the other hand, it's just polarization of the electron cloud. There is hardly any fixed charges or traps and so on. So it's a very different mechanism of polarization. So the other topic which I think has quite a lot of relevance is how much the electrostatics of the molecule is changing upon absorption. So that when the molecules are absorbed to the surface, they basically change their nature. And yeah, that's more or less. So we are talking, as I showed before, about two different contacts or two different interfaces. We have the interface with the substrate, which is normally by chemical binding, not necessarily. And there is the interface with the top contact, which is a much weaker binding. And I would like to show that in both interfaces, we see this change of polarization. And again, my goal here would be to give general perspective, not a very detailed, because I don't think we have a good theory how this really happens. So this is quite known that if I'm talking about the potential drop or the dipole over the monolayer, it's normally divided into contribution from the bonding and contribution for the molecule. So I would like, so before I show these modified styrene, which have a very high dipole by themselves. Now I want to ignore this dipole of the molecule, and for that I will show alkyls. So alkyl chain should be relatively non-polarized, and I would like now to consider only this extra dipole forming by the binding. So normally when I show it in a live audience, I would ask, so if we have alkyl thiols adsorbed to gold, would it decrease the work function or increase the work function? So there could be arguments for both sides. The simplest argument is that the gold sulfur bond has a negative charge on the sulfur. We can see it from XPS. So if we have this C9 dithiol, the top thiol, which is not binded, is 0, and the one that is bound to the gold is negatively charged. So this kind of dipole with negative charge on the sulfur should increase the work function, and by my convention, okay? However, one of the very early works on this field by Cohen group from 97, I think, yeah, 97, they made a set of these molecules. These molecules have 2 arms, and they are bound by disulfide to gold, and they can change the dipole. If you see the point here, it's a bit busy plot. But this trend line does not cross 0. This is the 0, 0 point. So this trend line crosses below 0. And this is the molecule with 2 alkyl chain. Okay, the R2 is with 2 alkyl chain. And we see that this molecule that's supposed to have 0 dipole or close to 0 dipole reduces the work function of gold by half an electron volt. Half an electron volt is a lot. And this was okay, so first of all, it reduces. My question before, so alkyl thiols on gold reduces the work function of gold. So there must be, this ionization is there. The ionization of the bond is there, but in addition, there is another mechanism that somehow reduces the network function. And the question I want to ask is, what is this mechanism? Because this is something we understand. Ionization, we understand. But what is this mysterious mechanism that makes the opposite change? So first of all, it was not accidental. There are a lot of other works showing this. This is the work, again, from the Netherlands, where they took gold and silver, and they absorbed either fluorinated alkyl thiol. So the fluorinated, because of fluor is negatively charged, it increased the work function. This is the gold and silver with about half an electron volt, I think, difference in their work in clean work function, and they absorb alkyl, so C6 in alkyl. So the alkyl thiols decrease the work function, as I said. But the interesting thing is that after absorption, the work function is the same. Here, almost the same with the fluorinated, it's the same regardless of the half electron volt difference in the work function of starting materials. Later, Frisbee also measured with different sets of molecules. Here I show one example with anthracene thiol on silver, on gold, and on platinum. And what they show here is the difference, not the final, just the difference. And they see that the difference is changing with the metal. That's also shown here. So we can think, okay, maybe the bonding is different because here it's a sulfur silver or sulfur gold. That's just the binding. But if that was the case, then we expected to the change here would scale with the electronegativity of the metal, but it doesn't. This is what's shown here. So it's not the bond itself. Again, it's something larger. So I'm asking, what is the driving force for this extra potential drop? So it's clearly a metal work function. We see it here. It's scaled with the metal work function. But what is the other characteristic of the molecule that's make this difference? So I would like to argue, I speculate that this is the chemical potential of the electrons in the molecule, and I will explain it. So the chemical potential, electrochemical potential is often, it's easy to connect to the Mulliken electronegativity, which is basically the average between the lowest unoccupied level and the highest occupied level. Okay, just the mean of these two would be the electronegativity of the molecule. Now, if we want to maintain equilibrium, if that would be a metal, electron would go from the metal to the higher work function to maintain equilibrium. But molecules do not have electrons here. This is a fictitious level. There are no states or electrons at this electronegativity. So we cannot maintain equilibrium just by moving electron. So the mechanism by which this happens is just polarization of the interface. So the interface becomes polarizable, so electron cloud will shift a little bit to maintain this equilibrium, but we'll see that it's really happens. So this is not a mechanism that is very well known, but it's apparently working there. Again, computation from Zoyer group, what this plot show is the change in the electron density after absorption. And there is a really fluctuating electron density change. And we see that toward the external side, it's positive, and the internal is negative. And that's really this direction of reduction. So because of this change in the electron density, we see this downward dipole. And there is a very interesting consequence for this, because that means that if we just put alkyl on the surface, the network function we'll see at the end would be just the electrochemical potential. Regardless, they don't care what is the metal behind them. They would show their electrochemical potential as the Fermi level. And we also tested it with silicon. So silicon is nice because it cancels out the effect of the binding, because the bond would be always carbon. This is again similar to what I showed with the styrene, just alkyls, 6C10 alkyls on silicon, direct binding. But with the same interface chemistry, I can change the work function by the doping. By changing the doping of the silicon, we can shift, and again, the gap is 1 electron volt. We can shift the Fermi energy by 0.9 electron volt. And we ask ourselves, what dictates the final work function? Is it the chemical potential of the molecule, or the molecule has some fixed dipole on it, or a molecule and a bond to the silicon? So again, energy diagram. So according to the first scenario, if we have a fixed dipole on the molecule, then the N-type dope, the Fermi level is much higher. So we will measure a small work function after binding. So regardless if it's P or N, there would be a reduction in work function. So the work function of P-type should be about 0.9 electron volt larger than the N-type. However, if it's a potential balance, then the potential drop would change in order to bring the chemical potential of the molecules to the Fermi level. So in the case of N-type, we will have an upward, and in the case of P-type, we'll have a downward. And what we measure, what we'll see at the end will be the same work function. So after absorption, regardless of the work function we started with, we'll see the same work function. And this is the results of the measurement with the UPS, here not with Kelvin probe. So this is the work function after adsorption. And these are the changes in it's relative to the edge, but so you see that we have a span of almost 1 electron volt, and the work function was roughly constant, except of this sample, it was more or less constant around 4, regardless what was the work function of the silicon. And surprisingly, this is also around 4. This is also the value that the Boer and others found on gold, okay, on gold and silver. So almost for all metals, we can say that the work function of alkyl thiols is around 4, and they can stabilize it by a mechanism which does not involve ionization. There is some other mechanism, nothing can be ionized in alkyl thiols. And if the sulfur is ionized, it's the opposite direction. So I also want to show that some of this effect can happen with the top contact, a little less. That's what I showed. This is the system that I already showed before with the modified styrene. And we see that the barrier, the Schottky barrier height, decreases with the work function. That's what we expect here. We expect from the formula, because it's N-type, we accept this inverse relation. However, when we change a little bit the system, that's now the substituent is buried underneath the phenyl, with a little different substituent, but the same principle. We see that there is a change, a little less change than what we saw here. But when it translated to when we make the same plot, it's not, the trend is lost. So what happened between here and here? So what we argue that for this system with the phenyl externally standing, their polarization is affected by the top contact. So if there is a polarizable group at the outer side, it will be affected by the top contact. And now if we take the same SBH that we extract, that plot it against the ionization potential of these molecules on the surface, we got it from UPS again. So from the UPS, we deduce the ionization potential, and we see now it's a very nice correlation. So these molecules are capable to become polarizable by the top contact. It's not always happen, so this is more tricky. This effect is not always there. And we speculate that it's related to the polarizability of the outer group. So it's really on the angstrom level. If the very outer surface is relatively hard, less polarizable, we will not see a change in the dipole. However, if we have a polarizable group pointing outward, it will exchange polarization with the top contact, even without a chemical bond, even in this physics of contact. So to summarize this, I think I have a few more minutes for the last section. Okay, so we show that there is massive changes in the dipole upon binding. The molecular dipole is really, it's very strong, but it's also affected by the substrate. It's not independent of it. It doesn't require chemical binding. This effect of changing is not only due to chemical binding, but it needs to be soft, the interface. The driving force is the balancing of chemical potential of the molecule with the Fermi level, not the bond. So it's, again, this effect was known in the literature for a long time, but people call it bond dipole. So it's not bond in the chemical sense, because it equilibrates with the macroscopic property of the substrate. And again, the mechanism is not well understood. I think people see it in DFT, but there is no like a simple theory to explain it. But it's some shifts in the electron cloud, like we know polarons in organic material and so on. And yes, and in some interfaces, it doesn't. Although there is a driving force, there could be a situation where the system does not have enough polarizability to make this balance. It remains imbalance. So if I said that the work function of the metal is changing so much the molecule, so now what would happen? So all these fields of molecular electronics, we basically apply voltage. So applying voltage is like changing the Fermi level of the substrate. So according to this thinking, the molecules should be very sensitive to the voltage applied on them. If we now think about more traditional molecular electronics, that would be my last topic. So how much the external voltage change the molecular transmittance? That's again, that would be my last topic. And as the way you see it, I worked a lot with diodes, like these Schottky diodes. And in electronics, there is a this is the current voltage behavior, it can be fitted to a model called the diode equation. And this is for years, and everyone doing this, it has a simpler model that the data can be fitted to. But when I start to work on a molecule-metal junction without the semiconductor, there was no such a standard equation. There were very complicated integrals and relations, but there was no simple relation, parametric relation that we can use as a guideline for data analysis. And there is a fundamental or philosophical problem here. That if this is more like a philosophical slide. Reality is the details in this macroscopic atomic junction. We don't know all the details. We don't know the position of all atoms and so on. So the theory, by definition, if it's not DFT, is doing some simplification, and it cannot really cover the entire details of reality. And then what I want to say that observation is even smaller. So a lot of time what we measure is a combination of a lot of different parameters, and we cannot really by the observation itself understand the details of get enough insight, what is going on. But one thing that we kind of know is that if the system is very narrow, the distance is small, it will behave like tunneling. And as the transport distance gets longer, we are moving to hopping. And these are the general, again, I'm not sure how knowledge is the audience, but tunneling is a quantum mechanical effect. That there is an electron wave function that's decayed below the barrier. Even electrons that don't have enough energy to go above the barrier, they can decay through the barrier. This is what we call tunneling. And the barrier here, I would symbol by epsilon. That's the barrier height in energy. Again, it's an energy diagram here. That would be the left electrode and the right electrode, and electrons crosses from side to side. And the hopping, there are different flavors for hopping, but the idea is that the electron is coming and residing for some transient time on the molecule. It can reside in one site or in multiple sites. Okay. But I will focus on tunneling because most of the molecular junction shows tunneling. But also tunneling can come in different flavors. So there is one approach is called WKB, and a lot of people also know it as the Simmons model. And the main characteristic of this model is that the electron is delocalized. It's all over the place. It's not localized to a specific point in space. The other very popular model is what's called Landauer, and the basic assumption in this model is that there is a very small restriction, so the electron is confined to a spot much smaller than the wavelengths of the electron. And this is typical for break junctions. For the large area molecular electronics, we don't really know. We don't know if because of roughness the electron is localized, or we can think of it as a delocalized wave. And there is a super exchange, which is some other variant. And in addition to this different description of the electron wave function, we have a very fundamental question where the voltage drops. So when we apply voltage, we can follow two different scenarios. Either the contact of a resistor, again, this is one electrode, this is the other electrode, and we put a voltage difference between them. So one scenario is to assume that the voltage across the molecule is constant, and all the voltage drops at the interfaces, on the contacts. And the other approach is that voltage is distributed along the entire distance. And this is the underlying assumption of Landauer and Simmons, but it's not necessarily mandatory. This is just what people normally assume, but it's not. I guess we can also do some mixing between these two variants. This is but I would like to show how I can get a little insight about this potential distribution from the analysis of IV curves. So to explain a little bit the concept, so the first thing to realize is that tunneling behavior is scaled, meaning that if I divide the current by some constant and the voltage by some constant, they would all fall on a general curve. Okay. So I can find this parameter that's all tunneling curves will behave very similarly. This is a bit disappointing because it makes it difficult to identify fine details. That's my work, and later also Baldia and Frisbee find the same. But this implies that basically the only information we can get from this curve is these two parameters. These two scaling parameters is the only information that we can get from these curves, unless they show some features. And interestingly, also simulation by these different models, also for a large extent, moderate voltages, they fall on the same general line. So it's not only very different. So this is experimental data from very different molecular junction in size and so on, and also simulation. So very different models, they all fall on this general curve at low voltages. So how this trick works? Again, so I divide it to two typical parameters. Let's start from the first one, which I call the magnitude. And it's basically, instead of zero current, I will call it equilibrium conductance, meaning the conductance at zero voltage, time this voltage scaling. And I give an example from collaboration with our moderator, Chris Nyhaus, where they use a junction with alkyl tiles covered by carbon paint. That was the special trick here. And we are playing with the lengths of these alkyl chains. So these alkyl chains come in different lengths. This is how the current voltage looks like with the different thickness of the alkyl chains. And again, it's in a semi-logarithmic plot. So we have orders of magnitude difference in the conductance with the lengths. And now if I plot it on a linear scale, because of this orders of magnitude difference, the slopes are very different. But I can just extract the slope by fitting the region near zero voltage. Okay, that's the lines here. This is just the slope. That's what I will call it the equilibrium conductance. And now I can just plot these values extracted for the different lengths. And we see the nice tunneling decay. This is what expected from tunneling behavior. So basically, the entire tunneling decay is in this magnitude parameter. All the length effect comes into this tunnel, not all, but most of it. So that's the first parameter, which is quite easy. Just the slope, this is easy to do. But as you can see here on the side, as we go to larger voltages, there is a deviation. So the experimental data deviates from this simple resistor. And the question is now, how can we quantify this deviation from linearity? So the linear is just this magnitude, and now we are asking how much the voltage is affecting. That would be measure of this deviation here. And there are basically two methods. I will briefly, I'm not sure if I have enough time. Transition voltage spectroscopy is more popular, but I think it has not so good theoretical basis, and I like the Taylor expansion. They rather converge. It's just a different explanation. So I will start with describing transition voltage spectroscopy. It's a plot of log of current divided by V square, and it shows this minimum. If we plot the current measure in this coordinates, it shows a minimum. And this minimum, the voltage where this minimum occurs, is called the transition voltage, okay? And what Frisbee, this method developed by Daniel Frisbee, and he showed a very nice correlation between the transition voltage and the homo-level position as deduced from UPS. So it's a very nice indication that this is a real parameter that is related to molecular properties, okay? So this is a very strong merit of transition voltage spectroscopy. Another advantage of it that it does not depend on the current magnitude. As we saw earlier, the current magnitude can change by orders of magnitude, and still this transition voltage can be extracted regardless of the magnitude. The disadvantage of the transition voltage spectroscopy, that's depending on the mechanism. So if we do this analysis by different transport models, we'll get different interpretation of what is the meaning of the transition voltage. So the most common one is to analyze it using the Landauer mechanism. And with the Landauer mechanism and the transmission like a Lorentzian, the transmission function behaving like a Lorentzian, we have a nice relation between the transition voltage and the energy barriers of transfer. But if we put here other models, we'll have other relations. If we specifically put the parabolic model, which I'll discuss next, we get the transition voltage is exactly this V0 that's I showed before. Okay, so these are the two extremes, and in between there could be a lot of other functions. So the parabolic relation is basically, again, not really new, from 69. And this is from a textbook on tunneling. And they is arguing that there is the characteristic of tunneling are exponential thickness dependence that we already know. That's what I showed before with the equilibrium conductance. There is a temperature weak dependence. And they also quote the parabolic dIdt. So the conductance should behave parabolically with the voltage. And this is basically comes from Taylor expansion. So we take the conductance and expand it around 0 voltage. So what I would like to argue that this first term in the Taylor expansion, that would be our G equilibrium that I extracted before. And the third term would give me this scaling voltage. And this linear term is normally very small because the process is symmetric. And again, I just tried it. And this paper, but Brinkman, Dines, and Roel was based on a WKB approach, like Simon's light approach. But actually, we can apply the same logic on different models, on Landauer and so on, and it will all behave rather as parabolic. Yeah, okay, so and the last, I think I'm just, okay, so this is a comparison between the Fowler-Norden presentation, which is supposed to show a minimum. Not always it shows a minimum, it's the same data that I used before with these alkyl thiols. So for the shorter one, the C8, we just cannot see a minimum with this Fowler-Norden. However, if I use this kind of analysis where I take the log derivative, it's called normalized differential conductance. It brings all the data to the same scale. It scales out the G equilibrium, and we see very qualitative. It's a qualitative way to assess the IV. And when this NDC crosses 2, is identical to the voltage where we see a minimum here. This can be shown mathematically that the point here and here, they are mathematically identical. So I will show now, again, the same system that what I showed before, the change of equilibrium conductance with the decay with distance. And we can also extract the scaling voltage from the NDC. And we see that the scaling voltage reduces with a reciprocal of number of carbon. This is a reciprocal scale. And if you remember before, I showed these two possible voltage divisions. So if the voltage falls only on the contact, we don't expect it to change the molecular energy levels. And there, in this scenario, the scaling voltage should be independent of the length. Or if the voltage falls on the molecules, the electric field will change for different lengths. As the molecule is longer, there is weaker electric field. And that's, in this case, we expect the V0 to decrease with the length. And this is more or less the qualitative. You see, it's reciprocal with lengths. This is what's shown here. So this is basically an indication that indeed the voltage falls on the molecules and not on the contact for this case. In other cases, it could differ. One last slide to show the power of NDC. So in hopping in general, people look on the temperature dependence, but we actually know that hopping should also depend exponentially on the voltage. And if it depends exponentially on the voltage, we're supposed to see a very sharp NDC plot, because this exponential of the current would look linear in NDC, and this is the derivative of log. Okay, and So this is a comparison between the red is for a hopping model and the blue is for a tunneling model. This is a simulation. So we see that for tunneling, this is a different scale. This is very small. It's only milli-electron volt. So the temperature dependence is very small. And also the voltage, the NDC is very flat. However, for hopping, the NDC should be linear and high. And this is what we've shown with Shiyu, another the panel. That's when they made a monolayer of anthracene with either monoamine binding or diamine. The NDC changes a lot. So this is the top is the current. ADA is the diamine. And by increasing this is the increasing force. Okay, we increase the force, the top contact penetrate and make the monolayer thinner and thinner. So we have exponentially larger current. But what we see here, that with the weak force, we have a very strong NDC. The NDC is linear and high. And as we damage this layer and make it thinner, the NDC becomes tunneling-like. So we are arguing that upon pressure, this interface is ruined. And just by ruining this interface, we change the complete transport mechanism from hopping-like into tunneling-like. However, when there is no top amine and there is no water layer here, the current slightly decreasing, but the NDC is the same. So the NDC is all the time tunneling if there is no amine at the top. So the NDC is all the time tunneling. And again, a feature that we can see from this voltage analysis. That will be the last slide, I think. So I wanted to show that interface polarization is an extremely powerful way to tailor device behavior. I think this is a lot of potential with 2D materials, with nanomaterials, a lot of room there. And I wish to advocate this model-free parametric analysis of current voltage that can help us to discern between the models and to learn information that we don't have to assume. And thank you for your attention.
Yeah, absolutely fabulous, Ayelet. Thank you very much for your beautiful talk. I already introduced all panel members, so I think we can immediately switch to the discussion. Yeah. So I think I would like to give Yoshi the opportunity to ask the first question and to open a discussion.
Okay, so I suppose to start from the first section of your talk, or I can pick up anyone in it. Hello, can you hear me?
Yeah.
Yes, we can hear you loudly.
Okay, so probably I am more interested in the second section of the talk because it's really like important aspect for the molecular electronics, because we have to really consider the surface dipole and how the energy barrier change, so that the property and the conductance of the monolayer. So I noticed one slide in your talk, you mentioned that the experimental study showed that when the thiol is bound to the gold, you have more negative charge on the thiol. That's kind of a counterintuitive to the chemistry understanding of the sulfur-gold bond. Basically, from the chemistry redox idea, the interaction between sulfur and the gold should be the sulfur has like a lone pair electron, and that will coordinate with the gold and then form the sulfur-gold bond. And in that situation, I would like to assume that the sulfur may take some positive charge instead of a negative charge. So I have some like a difficult time to understand that the one that you showed that the sulfur has some negative charge. Because if you think about it from chemistry point of view, the sulfur and the thiol, which is the bond between hydrogen and sulfur. Probably you can call that a kind of a reduced state of sulfur. That's generally what we believe in for the thiol. And when the thiol is connected to another thiol which has the dicyl bond, and that is already called the oxidation state of the thiol, right? If you think about it, you're changing from thiol to dicyl. You use some oxidizer to oxidize the thiol into dicyl. And then if you think about the thiol bound to the gold, I would like to say that assume that is even more deep oxidation of the thiol, which I naively believe that sulfur should take some positive charge. So it's kind of not very easy to capture the idea. Do you have any comments on that?
I must admit that this is not my strengths. The organometallics, I'm not very familiar with that. I am quite certain about the XPS, that this is the common interpretation. But yeah, maybe Chris can tell more about this. I thought this is kind of well known that the sulfur is negatively charged, but I might be wrong. Anyway, the analysis that I made, especially, I think the strongest indication is maybe I was wrong here in the detail, but the fact that there is a dipole that is formed by the work function of the substrate, this is, I think, beyond doubt.
Yeah, but I think you make a good point, Ayelet. I think with the method of thiolate chemistry, there are some unclarities about the exact binding structure. And I think also from, depending on the procedure, the interface may change a little bit. And you can also find review papers on this topic, that the binding chemistry can vary a lot from exactly how the thiol is connected to the molecule. So I think the way to go is indeed to look at the XPS and simply look at the shifts. Then you really have the answer for that system. So that gives you really an independent idea how the energy alignment looks like. And of course, the same you can do with UPS or Kelvin probe spectroscopy, for instance. So yeah, I think experimental determination is very important. Yeah. For instance, we have done a lot with impurities on surfaces. And we saw already that when we make surfaces rough, we get disorder in the monolayer, and that also affects the effective energy level alignment, meaning the one you measure. And when you would look at the structure, you can get very different answers. And we have also found very different answers when we derive monolayers from their respective free thiols, thioacetates, or disulfides. While on paper, they should all make the same kind of monolayer. But from our measurements, we saw quite substantial experimental differences there. Yeah. So you have, does that answer your concern, CU?
Well, probably I have to check more literature because I'm trying to understand it from the chemistry point of view. It's kind of counterintuitive. It looks like there's really something that we should really try to find out the alignment between the chemistry intuition and the experimental observation. Yeah, I think there's still many chemistry question in these molecular junctions. Yeah.
Yeah, certainly. Okay, then maybe we move on to our next panel member, Golan.
Hi, Chris. Hi, Ayelet. It's a nice talk. Here, I may have some similar question. Here in your talk, it's mainly talk about the dipole moment and the chemical potential that mainly change the energy diagram, and then can explain on how the charge transport via the molecule. Actually, recently we did some work on the monolayer, we just make some slight change on the monolayer, such as protonation or deprotonation. It's a very simple chemical reaction.
First, well, again, there is limited time, so there was a lot of works, I think, with effect of changing dipole in a metal molecule metal junction. And there the results are kind of mixed. But I think most of the work did not see large effect. So when we don't have the semiconductor behind, I think in general the effect is smaller and is also less consistent. So what I think that I try to make this point quite clear. That's we need the semiconductor behind it as an amplifier of this electrostatic effect. Now, you are correct that when you measure UPS, this is the free surface. And as we put the top contact, then if, for example, you have protonated that and even put their positive charge, maybe now this positive charge will be balanced by the top contact. Even if it's not really charging, but maybe there will be like screening or image charge or something like that on the top contact that will sort of cancel or diminish the effect that you observe on the free surface. So these are two things. First of all, I'm not so sure that the electric field is enough to modify the transport if there is no semiconductor behind it. And second, for sure, we know that there could be a different situation between an interface and the surface. The problem is that we don't have good sum rules to predict it. So I try to show that relatively we can say that the more polarizable is the outer group, we will see a larger change. The top contact will change a lot when the outer group is polarizable. But I cannot say that we fully understand it, and there is, again, a lot of place to further study what control the charge balance with the top contact. So it exists there, but it's less predictable than with the bottom contact.
Okay, thanks. So probably we need to think about some new method.
Yeah.
But if I can chime in a little bit, have you looked at the correlation of your behavior with surface roughness at all? Because that's one thing that surface roughness, because we overlook surface roughness quite a bit in our measurements. And there are a lot of papers out in literature that people never characterize the substrates they're using, and sometimes the data is all over the place.
Yes, I mean, it's a very good point. So generally what we try to do is to work as smooth as possible. So we try to bypass this problem just working with that's also one advantage of silicon, that you can make it fairly smooth. But it's true that it could be very interesting, I mean, to understand at which point the order, of course, that if this array would be disorder, the effect would lose. So we need the dipole to be aligned in order to see this effect. So roughness, if we can control roughness and see how it changed, that could be very interesting. I think I didn't understand you quite well. So at the beginning, you said about plasma. So plasmons and all this Raman spectroscopy, I think it's another way that could be very interesting, because these are electrostatic shifts. We should see it in these Raman shifts, and that could be another, like what Tsunan asked before, about additional to UPS. try to understand internal fields with spectroscopy. That could also be very interesting.
But now you mentioned plasmons. The tunneling current itself will also excite plasmons inside the junction. So you get also, these optical field enhanced effects.
So
How do you think that will affect the measurements?
Yeah.
Yeah.
On the very smooth surface, can also get a strong plasmonic effect.
Yeah, because the inelastic component of the tunneling can excite the plasmons. However, you need some kind of roughness or a defect, or maybe you make a nanoparticle or whatever mechanism to outcouple those plasmons in the form of photons. Otherwise, most of the plasmons will just dissipate as heat. But since we are talking about these kind of effects, you also mentioned that 1 nanometer layer of molecules can affect more of 100 nanometer of sparse space charge region. And these space charge regions can be hundreds of nanometers. That sounds like a very long range effect to me. What is the mechanism behind that? Where does this come from?
It's this energy balance. It's amazing how strong it is. But I think intuitively we think about molecules as something that is fragile, it's not like concrete or this inorganic thing. But in terms of electrostatics, they are the strong features. The issue is most solids would have some free carriers. And the fact that molecules do not have free carriers, that's, I think, why make them so strong, because they are much less polarizable, I think, than
okay, but also polarizable. We have gigavolt per meter electric fields in these kind of nanometer regions. They're really, really massive. And I think at some point, if you polarize a molecule enough, you will literally break the bond, right? But it doesn't seem we see those kind of things, because after all, the junctions are stable. We are just here in a lucky spot, or how come we don't break the junctions all the time, though we seem to polarize the molecules a lot?
I do think, one of the things that's I plan to do, I didn't do for. So it occurred to me, I think I listened to your talk. You talk about nerves, the nervous system. So this potential on the nerves, on any cell membrane, there is like 70 milli-electron volt, but constant. On any cell membrane, it holds 70 milli-electron volt. This is nature. And this is quite high field. If you translate it to the distance, it's huge field. And that's in biology is very common. I'm not so sure what are what conclusion can we draw, or how can we translate it to our technology? But there is also a lot of interesting works with, I think now with protein and enzymes. They are saying that people start arguing that much of the activity of the enzyme core, or the spot where the chemistry occurs, is by polarizing. So in this core where the enzyme activity occurs, because there is the structure induces very high field in this spot, which stabilizes the transition state. So I think this is how these huge fields are nature of molecules.
That's pretty amazing. Anybody else? Some more questions?
Sure. I
have time enough.
Yep. Ayelet, I can ask one question. In your discussion about the alkene I noticed that you work with the even-numbered alkene, and I was wondering, even-numbered, you work with 2, 4, 6, 8. Like,
yes. That's increased work. I just do the analysis.
So why not the odds? Well, why not
really
odd numbered?
Does it make a better monolayer? I don't know.
Because Chris and I have this thing on odd-even effect that we started a while back, and it has been fascinating that a single change in parity changes the conductance, for example. And when I saw the data, I was like, is there anything that you've seen with the odds that maybe was different, or is it just by choice that you didn't look at them, or because I would expect the contact behavior to be a little bit different.
Yeah, for many molecules, the evens are commercially available and the odds aren't.
Okay.
That could be a very practical reason, I think.
I think
it
we're
makes
missing
sense
two.
because the top methyl is polarized. So the terminal methyl is polarized, and its angle is expected to change the work function. Yes.
Yeah, so I'll be curious to see how they look like. I think we're missing the 13 and 17 commercially, but the others are available. It'll be interesting to see how such a small shift would affect your results. Yeah.
Okay, maybe I'm still a bit fascinated by this, and I have maybe a little bit more complicated question, or maybe a simple question to ask, but maybe very difficult to answer. Well, in the community, I think we are fascinated that there are quite a few molecules, especially biomolecules. They seem to support activationless transport over very long distances. Biological systems may be much more polarizable than the typical alkyl functionalized monolayers that has been studied so far. But compounded by studies, also by some of the papers by the people you cited early on, especially organized systems and monolayers that are perpendicular, they can have very high dielectric constants too. How do I fit these now in context? Do you think these kind of polarization effects could play a big role in this fascinating phenomenon of long-term, long-range tunneling, or are these completely unrelated phenomena?
Well, how to say? My intuition says that it is highly related. It's difficult to say if there is really like a polar one that is forming there, but I think in general, like Marcus theory was developed for solution where it's always the solvent that's polarized. But here, the fact that we have such a dense array, this is something that is not in solution, but we have a very dense array of neighbor molecules. So the polarization in this neighbor molecule could be extremely important, and I'm not sure if there is a very detailed theory on that. I quote there the papers from Lior Prony, and there they really discuss it that a neighbor molecule reduced the dipole. So the polarizability of neighbor molecule normally works to reduce the net dipole, but how much it's my intuition that it would stabilize an extra electron on if we transport electrons. So this polarizability of the matrix can help. But
because I can imagine a polarizable system can accommodate a charge carrier much better than a non-polarizable system. So even though molecules are not redox active, formally speaking, they may still be able to hold charge, blurring the two worlds between separating coherent and incoherent tunneling. Yeah, so although maybe you measure a very weak or non-existing temperature dependency, doesn't mean that maybe the truth is a little bit in the middle, not completely coherent, but also not completely incoherent.
Yeah, in general, this is part of my motivation to do this assumption-free models, because I think we are quite far from the reality. We are guessing the models.
No, fascinating, and I think these things can have far-reaching applications, implications in other areas of research as well. Basically, any research area that involves heterogeneous charge transfer, right?
Yeah.
I think we are getting almost to an end. So unless there is an important question, no, then I would like to thank Ayelet and all panel members one more time. And then I would also hand out to Ayelet this very nice token of appreciation for her contribution of today. Yeah. So thank you very much.
Thank you for inviting me.
Yeah. So then I would like to make a small little advertisement. Next week, Kouros Kalantar from the University of Sydney will be talking about green reactions and catalysis in liquid metals. And I think that will be a fantastic contribution as well. So hopefully most of you I will see next week again. And then I would like to thank you all for listening, and hopefully we'll all tune in next week again too. Bye-bye.
Bye-bye. Super. Learn a lot. Yes. Okay, cool.
Very good.
Okay. Have a nice weekend.
Have a good one.
Nice weekend.
Yeah.
Bye, Grace.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can。能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。
乐！该吹蜡烛了，
来，我帮你。啊！
祝你生日快乐！
生日快乐！
好漂亮的花，我很喜欢。
这是我的礼物，多层陶瓷电容器。
哇，这是多层陶瓷电容器吗？
失败了，
没新意。那个我的也是啊。
哇塞，这个不是太阳用电的多层陶瓷电容器吗？小型、大容量，从原材料开始研发，性能和质量都有保证。我最想要的就是这个了，太阳用电的多层陶瓷电容器。
你没事吧？
机长，还是你最了解我，有了它让我变得更好。我们是彼此需要的关系。